Hello friends, welcome to our first video in multiple angle and product to sum formulas. And I know that you're like looking forward to this. This is so exciting because we're going to talk about proofs. But I do think they're algebraic. They're not near as geometric or they're pretty intuitive. And if you're wondering why are we even bothering with this, like just give me the formulas and I am. You will not have to memorize any of the formulas that we derive in this video. But overall, I think it's important for you to know how to get them because these are not on the AP. Even though I'm not requiring you to have these memorized for any kind of assessment, they are not on the AP. You will have to use them on the AP. And I want you to see how they build from each other so that if you know sine, cosine, cosine, sine, cosine, I don't know what kind of S that was, cosine, cosine, sine, sine, if you know that, you're going to be able to derive the rest of the formulas if you're in a pickle and you can't remember them. So that's really what the purpose of this is for. So how are these double angle, power reducing, half angle, and product to sum formulas derived? All right, so here's what we know. If I'm asking you to find the sine of 2u, and again, we use that u because you can represent any functions. So the sine of 2u, well, we can consider this to be the sine of u plus u. Well, now all of the formulas I learned in the last lesson kicked in. So this is a sine, so we have sine, cosine, cosine, sine. And then we do u, and u. And because this is the sine, we take the same operation. And I'm going to write this out, but as a reminder, multiplication is commutative, so I can rewrite this term as the sine of u cosine u. And what we have left is 2 sine u cosine u. And if you're wondering, okay, that's fabulous. Why is this important? Why do we need to know this? Because basically what we're saying is if we're trying to find information about the double angle. So I'm just going to make up a number. Let's say that we know information about u being 17 degrees. If I know the sine of 17 degrees, if I know the cosine of 17 degrees, multiply those ratios together times 2, that will give me the sine of a 34-degree angle. So I'm able to find out information about an angle, does that make sense? Using essentially half of its angle. So I tend to, in notes, I call this the single angle, and we can use the single angle to find information about its double. All right, so cosine is kind of a hot mess because cosine, we have a lot of ways that we can talk about it. So we're going to start this the same way. We're going to start it as cosine, cosine, sine, sine. U. And because we're doing the cosine of u plus u, in cosine, we take an opposite operation. So this becomes the cosine squared of u minus the sine squared of u. And that is one iteration or one version of the double angle for cosine. Again, what does that mean? If you knew information about the cosine of 17 degrees and the sine of 17 degrees, this is a formula that will help us determine what the cosine of 34 degrees would be. All right, so now let's just concentrate on that double angle. What if I would instead rewrite the cosine squared using a Pythagorean identity of 1 minus the sine squared? So another iteration or another way that we can write the double angle formula is 1 minus 2 sine squared of the argument of u. Furthermore, if we go back, I already used red, if we go back, and again, I am looking at the original cosine squared u minus sine squared of u, well, I can go ahead and keep the cosine squared of u the same, but I can put in 1 minus cosine squared of u as a Pythagorean identity, and that gives me cosine squared of u minus 1 plus cosine squared of u. So when I combine like terms, I get 2 cosine squared of u minus 1. So if you're wondering, why do we need all three? Well, it just kind of depends on the problem and what you're given. But I will tell you that for our next grouping of formulas, you're going to need these two in order to get power reducing. So that's why we discuss them. Okay, and I think let's do tangent. Again, we can do the tangent of u plus the tan of u plus u, excuse me. And if we plug that into our double angle, or excuse me, if I plug that into the sum and difference for tangent in order to get my double angle for tangent, you get the tan of u plus the tan of u. And then I take an opposite operation and then I multiply them together. And so you can use the tangent of u plus the tan of u gets 2 tan u over 1s minus tangent squared of u. So that is how in your notes and on the reference sheet, which is a separate link on Schoology, this is how we derive those double angle formulas. All right, so the next video is going to discuss examples of how we apply the double angle formulas onto examples, how I do my homework problems. So next, let's talk about how we use those double angle formulas in order to call the power reducing. And I will let you know that these power reducing are used a lot in calculus. All right, so if we know that the cosine of 2 theta is equal to 1 minus 2 sine squared theta, I can write the, I want to solve for sine squared of theta. So to do that, we're going to subtract 1. So I get the cosine of 2 theta minus 1 is equal to negative 2 sine squared theta. I'm going to divide both sides by a negative 2. And we can assign our negative to be on top or in the numerator instead of the denominator. So often the way that you're going to see this printed is you're going to see it if I distribute this negative. It would be 1 minus the cosine of the double angle over 2. This is why it is called power reducing. On this right-hand side, you have sine, and it is to a power of 2. This is an expression we can substitute for it where we no longer have a power. It's a double angle, but this is still considered the first power of cosine. We're going to do the exact same process to the cosine of the double angle. Our goal is to get cosine squared by itself. So I am going to add 1 to both sides and then divide by 2. So this gives me the cosine of the double angle plus 1. So again, we have cosine. We have that in the first power because if I've got something that's cosine squared, and friends, you do have an opportunity, like there might be a problem where you have to use a Pythagorean identity. It is equivalent to 1 minus sine squared of theta, but 1 minus sine squared, let's put that down. 1 minus the sine squared, let me write it where you can see it better, maybe. 1 minus the sine squared of theta, that is still a power. It's a second power of sine. And many times we want the power out. So now you have an expression that is in the first power of cosine. All right, so the one thing we're going to do when we power reduce tangent squared, and let me get rid of this. When we want to do tangent, we aren't going to go back to a particular double angle formula. We're going to use what we learned in the past two power reducing derivations. So we know that the tangent squared of theta is equal to the sine squared of theta over the cosine squared of theta. If you power reduce the numerator, we get 1 minus cosine the double angle over 2. If we power reduce cosine squared, it is cosine of the double angle plus 1 over 2. And the 2's cancel. And this is how we come up with 1 minus the cosine of the double angle. And oftentimes this is written as 1 plus the cosine of the double angle when you actually look stuff up online. So this is how we are getting these power reducing formulas. All right, let's see what's next. What's next is going to be our half angle identities. So for our half angle identities, all right, what happens if we take the power reducing formulas and substitute x with x over 2? All right, so if I go ahead and I do the power reducing sine squared of theta, or since we're dealing with x's, let's stay with x's. Sine squared of x is equal to 1 minus the cosine of the double angle over 2. And what I'm going to do is replace x with x over 2, and that should have been an x, so we're going to replace that argument with x over 2. We get that the sine squared of a half angle is equal to 1 minus the cosine, the 2's cancel, of x all over 2. And then to get the sine of the half angle all by itself, you take the square root of both sides, and we will discuss in the video after double angle is when we talk about half angle, that you are going to have to figure out if the sine of the half angle is a positive or negative value depending on what quadrant your half angle lives. And so the plus minus stays, and we get the square root of 1 minus cosine x over 2. So again, what does this allow us to do? This allows us that if we know information about 34 degrees, so if we know its sine or its tangent, or we have a picture of their triangle, we know information about a 34 degree angle, it's going to allow me to calculate the sine of a 17 degree angle. All right, let's talk about cosine. So again, we know that the cosine squared of x is equal to the cosine of 2x plus 1 all over 2 by power reducing. We are going to replace the x with a half angle. So the cosine of the half angle is equal to the cosine of x plus 1 over 2. Again, we take a square root. So the cosine of the half angle is equal to the positive, or, not and, but or, and you will have to pick out which sign it is based on where the half angle lives, of cosine x plus 1 over 2. Now, notice how you have the cosine, that the tangent is u over 2. How are we getting that? Well, if in order to get tangent, we would take the square root of 1 minus the cosine of u over 2, and then, actually, let me write this really big. 1 minus the cosine of u over 2 all over 1 plus the cosine of u over 2. Those cancel. And I'm left with 1 minus the cosine of u over 1 plus the cosine of u. And I'm not going to do both, but you get it by rationalizing. So you can multiply by the conjugate of the numerator or the denominator. So if I multiply by 1 minus the cosine of u over 1 minus the cosine of u, this is going to yield 1 minus the cosine of u squared all over 1 minus cosine squared of u. And then I can replace 1 minus the cosine squared of u with sine squared of u. And when you take their square roots, because both of these will always be positive. If you're squaring the numerator, that's a positive value. If you're squaring the denominator, it is a positive value. So you don't have to worry about any kind of like negative root coming out. So the square root of 1 minus cosine u is 1 minus cosine u, and the square root of sine squared is sine u. So that is where your tangent half angles are coming from. And just to spare time, if you wanted to know how we derived that second version, you would do the exact same thing, except you'd multiply the numerator and denominator by 1 plus cosine u underneath the radical. Okay, so now we're going to go down to our last grouping, which is the product to sum and sum to product. I'm going to be really transparent here. I'm only going to kind of do one of each. These aren't used a ton. They are not going to come up in calculus a ton, but I feel like for your tax dollars, I should at least like acknowledge where they come from. Again, these do not need to be memorized. So I would say understanding how sum and difference goes to double angle, goes to power reducing, goes to half angle, I do think there is a lot of merit in understanding that process in the event you are sitting in a college classroom on an AP and you're like, oh my gosh, I cannot remember what the power reducing formula is. For these product to sum and sum to product, I've always had a reference sheet. I've never personally, I don't even think I had to memorize them in college, but I just want to acknowledge where they come from. So again, if you don't mind, I'm only going to do number one. I think you're going to see the point and how we get there, and that hopefully will explain how we get the other formulas. All right, so how do we get there? We're going to keep the 1/2 on top, and what I'm going to do is, this is the sum and difference. So it's cosine, cosine, sine, sine, u, v, u, v. And because it's a subtract, we take the opposite operation. Then we're going to subtract that sum of a cosine. So that's another cosine, cosine, sine, sine, u, v, u, v. But it's going to be a subtract. All right, so this is kind of a hot mess. Let's see where it gets us. So I have the 1/2, and I'm going to get, well, if I distribute the negative, this is a subtract cosine u, cosine v. That's going to cancel out that cosine u, cosine v. When I distribute that subtract, or the two negatives, that's going to make this term a positive. That's a positive, so I have two of them. And then 1/2 times 2 gives me the sine u, sine of v. So that would be the process that gives you all of what we did. Is we took something that was a sum or a difference, and we just turned it into a product or a multiplication problem. All right, so again, I am kind of just, for the sake of your time and energy, you're welcome to, but even if we were in a face-to-face classroom situation, I usually do just kind of move on. All right, so that's where all of these come from. So what I just did is I showed you the product to sum formulas. This last grouping, I don't find it particularly intuitive. And if I want to be real honest with you, it's, I think, a hair convoluted, but they are true. And so we'll just take, 1 second here to kind of talk about how we go from sum to product. All right, and even if we were face-to-face, notice I only do one of these. So on these, what we're going to do is we're going to let u be x plus y over 2, and we're going to let v be x minus y over 2, and I'll have kids go y, and I'll tell you because you can, because I can let u and v be anything if it makes this work. So what we're going to do then is fill that into our expression here. So we have the sine of x plus y over 2, the sine of x minus y over 2, and that's going to equal, I'm going to write it below because I have a feeling, oh no, maybe I won't run out of space. Here we go. 1/2, and it's going to be the sine of, this is going to be x plus y, and since they're a common denominator, you're going to have plus x minus y, right, all over 2, plus, because this is going to be u plus v, all right, and then if I do u minus v over here, we're going to have x plus y minus an x minus y all over 2, and that is going to come behind a sign. So this gives me, all right, let's do a different color. All right, this is going to give me 2x plus 2y over 2, and I have a mistake. I did not write the trig function sign in front of it. So that's going to give me 2x plus 2y over 2 plus the sine of x plus y minus x plus y when I distribute that negative over 2. So that gives me 1/2. Well, if I factor out a 2 in that numerator, the 2's are going to cancel. And you know what? I just realized I have a mistake, and I feel really embarrassed about this, but I've been doing videos all day, and I don't feel like stopping and re-recording. So we're just going to back this truck up for just a minute, all right? And my just sincere apologies for this. Let's go here. I did not look closely at my plus y and my minus y, so I have to correct. that is going to just be a 2x. The y's will cancel, and that's 2x over 2. Again, my sincerest apologies. I hope you don't mind. We're in the pandemic, trying to throw this together, trying to do my best. I appreciate your patience because I know that you are working your rear ends off too. Okay, thanks. All right, so now that we have that completed, so again, we had to do a little math therapy, and there's 2x over 2. Remember, we have a classroom where mistakes are valued. So I make them all the time too. So the negative x and the x will cancel. So I will have the sine of x plus the sine of 2y over 2. And so this is how we derive 1/2 sine x plus sine y. And so again, I just did one, but that is how we are getting the sum to product formulas. So there is no assignment affiliated with this. You do need to turn in your notes for credit. I know that's silly, and you might think it's silly, but I have to find a way, we have to be accountable for our learning. But now I would go ahead and watch the double angle video. It really is just a lot of plugging and chugging numbers. So the fact that you don't have to memorize the formulas is a pretty nice deal. So thank you for bearing with me, and I hope you're having a great day.